So now we're moving on to what I would possibly call my favorite thing in math. So I used to mark provincial exams for the grade 12 level, and this is the question I always chose because there's a little bit of artistic license with these as long as you don't break any math laws, and they're just new. Everybody can do these a different way. But what we're going to be doing is giving lesson one a purpose. We are going to be proving trigonometric identities. So what that means is that you're going to have an equation that I'm going to tell you is true. So if you plug in any value of x, it will be true. But we're going to prove algebraically that the left side is equal to the right side without putting in a value of x. So we're going to use all those skills that we learned in lesson one to play with these expressions and make them equal to each other. So the way that we're going to do this is there's like 6 commonly known tricks that can help you solve a trigonometric identity. It's not like it's step 1, step 2, step 3. It's more like suggestions. Here's some things you could do. Sometimes you want to turn everything into sine and cosine. Sometimes you don't. Sometimes you'll look for glaring identities. Sometimes you won't. So you're going to approach a question and be like, can I? And if I don't know what to do, start with this, start with each one in turn until you can finally do something. So you will be given an equation, something like sine 2x is equal to 2 cotan x sine squared x. And we're going to start with tricks A and B together because it's kind of hard to separate the two, which is that we're going to change everything into sine x and cos x, and we're also going to be looking for glaring identities. Now, turning everything into sine x and cos x is something like here, you have a sine 2x. That's not a sine x. So we want to get rid of any of these double angle identities. And we also want to get rid of any of our like reciprocal and quotient identities. So anything that's not written as a sine or a cos, we want to use those identities to turn it into a sine and a cos. And then we'll talking about glaring identities as they pop up, but I will say these are generally our Pythagorean theorem identities. So here we go. We've got sine 2x. One thing I like to do is draw a line because when you're working with identities, even though it's an equation, you're never going to cross the center line. You're going to work with the left expression, you're going to work with the right expression, and you're never going to work with both doing the same thing. So on the left hand side, again, I see that double angle identity. So I'm going to replace sine 2x with 2 sine x cos x. And this is just coming straight off of your formula sheet. And in case anyone's forgotten what I mean, so right, you're looking for your double angle identity, which your identity is down here, and you see that sine 2x is equal to 2 sine x cos x. So that's what we've replaced it with. Then on the right hand side, I have a 2, and the only thing I want to change on this side is this cotan x. So when you look at your identities, okay, for cotan x, you're going to be looking at your reciprocal or your quotient identities. You could change cotan x into 1 over tan x, or you could change cotan x into cos x over sine x. Generally, this is the one we're going to choose because the first trick is to change everything into cos and sine. So let's replace cotan x with cos x over sine x. And then I'm going to keep sine squared x as a sine squared x. Squared's okay. 2x is not okay. Then hopefully everybody's looking at this and being like, oh, well, look, I can simplify. Sine squared x divided by sine x is just a sine x. And I would be left with 2 cos x sine x, but I'm going to use the commutative property of multiplication, which is that 2 times 3 is the same as 3 times 2, to write this as 2 sine x cos x. And then I encourage you to celebrate. As soon as your left expression is equal to your right expression, celebrate by, writing left side is equal to right side. Yay! Maybe putting a check mark, maybe putting a smiley face, or maybe being super geeky and putting QED, which I challenge you to look up what it means. I can't remember. It's Latin. Quantum eris determinatum or something. And it's like, thus it is proven or thus it is determined is what it means. I used to mark the provincial exams and there'd be a whole class of students that would write this. And I was like, what is that? I'm like, oh, it's Latin, obviously. All right, next question. I want you to pause the video and give this one a try. We learned how to do this in lesson 1. So for me, the right-hand side is as simplified as it's ever going to get. And then my left-hand side, I see my double angle identity again. So I'm going to replace this with 2 sine x cos x. And then inside the bracket, I'm going to change my tan x into sine x over cos x using my quotient identities. I'm trying to memorize the words. And then cotan x is cos x over sine x. And then I'm going to multiply through. Now, some people will multiply and simplify at the same time. Some people will write it as a multiplication, and some people will actually do the multiplication. It's kind of up to you. So you can write this as 2 sine x cos x times sine x over cos x plus 2 sine x cos x times cos x over sine x. Or you could multiply it and get 2 sine squared x cos x over cos x, or you could just simplify as you multiply through. It's kind of up to you. So I'm going to do the actual multiplication. I don't know why. I don't usually, but I'm going to do it. I feel like it's a little less writing. Over sine x. Then I'm going to simplify what I can. So here I notice that cos x divided by cos x is 1, and sine x divided by sine x is 1. So I'm left with 2 sine squared x plus 2 cos squared x. And I should also say this is that you have to be very intentional about your steps. In other words, don't skip steps. So some people might be like, oh, I could go all the way from here to, well, I mean, to here is okay, but the next step would not, like you couldn't go even further. What I want you to see now is that we're going to factor out the 2, right? Because my right-hand side is just a 2. These terms both share a greatest common factor of 2, so I'm going to factor it out, and I'm left with sine squared x plus cos squared x. Now, hopefully, because we've done lesson 1 in such great detail, you guys look at that and be like, oh, Pythagorean identity. What do I mean by that? Well, anytime I see squareds, I jump to my Pythagorean identities. Okay, and when I look at sine squared x plus cos squared x, I know it's equal to 1. So for this one, it would be 2 times 1, which is 2. And you'll notice me showing a lot more work with these than I sometimes do because you want to show, right? I mean, technically we should annotate these. What did I do? Well, I recognized a Pythagorean identity. How do I show that? Well, I replaced it with a 1. You know, something along those lines. Without putting words, can you show it in your math what you've done? And then again, I made left side equal to right side. I've gotten to a place where I like to check it. Yep, I'm good. All right, the next 2 examples are very similar. So again, I'm going to draw a line. And then you can pick with which side you want to start with. I keep drawing to the left-hand side first, because it tends to be the easier one in all of these questions. But when I look at the next one, I'm like, ugh, I want to work with the right-hand side first. It doesn't matter. So for this one, again, I see the double angle identity. So I'm going to replace it with 2 sine x cos x. And then I'm over 2 sine x. And then you can simplify. I am going to divide 2 by 2, sine x by sine x, and I get 1. So I am left with just a cos x. And now that gives me a goal. I'm like, okay, that's as simple as it's going to get. Now I'm going to try to turn my right-hand side into cos x. So how are we going to do this? Well, I can't change everything into sines and cosines because it's already done. So I have to move on. What about glaring identities? What does Karen mean by glaring identities? Again, usually Pythagorean identities. So anytime I see a 1 and a squared function or 2 squared function, I always think of Pythagorean identities. And this one's 1 minus sine squared x. So if I look at this one, if I minus sine squared x from both sides, I'd be left with a cos squared x. So I'm going to replace my numerator with just a cos squared x, and my denominator is a cos x. And when you start doing enough of these, you get kind of like a giddy feeling when you're so close. You're like, oh, I'm there. Cos squared x divided by cos x is just a cos x. Yay, I did it. And celebrate. And again, if you're looking at someone else's work, their left side and right side might not be the same as yours. It's not like the answer to this is cos x. The answer could be lots of things. I mean, you could have stopped here and somehow turned this guy into cos squared x over cos x, I guess by multiplying by cos x over cos x, but you could. There can be multiple answers as long as the left-hand side is identical to the right-hand side and you haven't made any math errors, you're fine. All right, let's look at this next one. This next one's a little bit trickier. So when I look at this one, my instinct is to start working on the right because look, it's another one of those double angle identities. So 2 sine x cos x, sweet, it's done. So now I know my goal. My goal is going to be to turn this left-hand side into 2 sine x cos x. Now there's a number of ways of getting there. How are we going to do it? Hopefully you've paused the video and given this a try. Anything you notice? For me, I'm noticing a lot of squared trig functions. So again, I'm thinking Pythagorean identities. In fact, I'm looking at this and thinking cos squared x plus sine squared x. That's probably a 1. So I'm going to replace it with a 1. This is not the only way to solve this problem. So I end up with 2 tan theta over 1 plus tan squared theta. Maybe you look at this and go, well, it's still a 1 and a squared trig function. Is this still a Pythagorean identity? Well, let's check. I don't have these ones all memorized, but there we go. 1 plus tan squared x is secant squared x. So let's replace it. We've got 2 tan theta over secant squared theta. Let me just make sure I didn't mess that up. Yes. I hate switching from page to page. Now what? Well, maybe I have to go back to trick A, which is to change everything into sines and cosines. So maybe now I go, okay, well, tan theta is sine theta over cos theta. And secant theta is 1 over cos theta. So secant squared theta is 1 over cos squared theta. And then I can divide. So it'd be 2 sine theta over cos theta divided by 1 over cos squared theta. So now I'm going to flip and multiply. So I've got 2 sine theta over cos theta times cos squared theta over 1. And now I can simplify. My cos theta divides evenly into my squared to leave me with 2 sine theta cos theta. Yay! And if you notice, oh, look at that. This guy I went for, oh, it's a problem in the question. I will go and retype that. Let's make that one a theta. Yeah, they won't do that to you. It's not like they'll use a different expression. I must have just retyped this and made a mistake. Just make these thetas or make all of these x's. Seems like a lot more work. All right, so now I have 2 sine theta cos theta and I am good to go. All right, so these next few examples are going to continue on with this idea of tricks A and B, which is changing everything to sines and cosines, as well as looking for glaring identities. Now, up until this point, we've talked about glaring identities being our Pythagorean identities, but that's not the end of the story. There is also, although very rarely seen, these sum and difference identities, which can be glaring. So I guess I feel like all of them are called glaring identities. You know, we talk about basic identities in terms of changing everything to sine and cosine, and then Pythagorean, sum and difference, and double angle identities. They could all be glaring, or changing everything into sines and cosines. They're kind of the same idea. So when I look at this one, I'm seeing this sum and difference identities. My right-hand side is as simple as it will ever get, and I'm going to work with my left-hand side. So over here, I have a sine sum identity. So it's going to go sine of the first angle, cos of the second angle, match the sine, cos of the first angle, sine of the second angle. Then to this, I am adding the sine of the first angle, cos of the second angle, match the sine, cos of the first angle, sine of the second angle. And then I look to see if I can collect like terms. I've got a sine x cos y and a sine x cos y. So I have 2 sine x cos y's. And then I have a cos x sine y minus a cos x sine y, which is gone. So look at that. One step and I'm done. All right, moving on to the next one. The next one, again, I put these into the lesson 1. I don't know if there was much practice in the homework on them, but mainly because of these 2 questions. So looking at this one again, I'm going to draw my line so that I work it one side at a time. And I look at my right-hand side and I'm thinking, that's pretty simplified. So let's work on the left-hand side. When I look at the left-hand side, I've got 1 plus, and then I hope you recognize that this is another one of those sum and difference identities. Now this one goes cos, cos, sine, sine, so I know it's a cos sum or difference identity. And then because it's a plus sign, if you look at your cos identities, if it's a plus sign, it's a difference identity. So the cos ones don't match. So it's going to be cos of 8 theta minus 6 theta. So now I've got 1 plus the cos of 2 theta, and I somehow have to turn it into this. Hopefully, I taught you well enough in lesson 1 that when you have a cos double angle identity, there'll often be that trick of eliminating the 1. There's also with this one a goal of knowing what I want, which is cos. So when I look at my cos double angle identities, my choices are cos squared x minus sine squared x, 1 minus 2 sine squared x, and 2 cos squared x minus 1. So there's a couple reasons I'm going to choose this. One, it's got a cos in it only, and the other one is it's got that idea of eliminating the 1. So I'm going to put in here 2 cos squared theta minus 1, because then I've got that 1 minus 1 that's gone, and I'm left with 2 cos squared theta. Yay! So that is the end of tricks A and B.